Hello, this is Yulin Yang. My topic is iCalib, Inertial Aided Multi-Sensor Calibration. This is a collaboration of University of Delaware, Army Research Lab, and Zhejiang University. Autonomous robots are equipped with multi-heterogeneous sensors like the IMU, camera, LiDAR, and wheel encoder. When the robots are exploring the environments, the camera will be used to get images. LiDAR will be used to get a sparse point cloud. IMU and wheel encoder will be used to get high-frequency pose estimate. In order to achieve this, we need both spatial and temporal calibration of these sensors. The spatial calibration refers to the radius transformation between these sensors. The temporal calibration refers to align the timeline of sensor, LiDAR, camera, and wheel to a timeline of IMU. There are quite a few work on multi-sensor calibration. For example, Calibrate. Calibrate can perform only IMU camera calibration. Cam.cal, MSG-cal, and LiDCalibrate. They are optimization-based algorithms, but they are only for sensor pair calibration. No time of flight calibration is performed for this toolbox. Mimic, Lake Fusion, and Vivo, they are filter-based methods. They only perform online calibration to improve pose estimation. However, iCalib can perform all spatial temporal calibration for all of these sensors. So we have two contributions. The first is we design iCalib, an initial calibration toolbox that can handle asynchronous IMU, multi-cameras, LiDAR, and wheel encoder. We also study the degenerate motion for multi-sensor calibration. Besides, we also investigate to use kinematics or bonding poses-based interpolation to handle asynchronous multi-sensor measurements. Why we are called iCalib? Because we use inertial information to build the pose backbone of the graph. We first integrate the base IMU at the camera frequency to build up the base VR graph. After that, we will collect the odometry readings between IMU poses and integrate them to build the odometry edge. When the camera observes the point landmarks, the image pixel edge will be added. When LiDAR observes the plane features, the LiDAR edge will be added. Whenever we add the odometry edge, camera edge, and LiDAR edge, the calibration will be involved. So for this graph, we can see that we will optimize all the historical IMU poses, all the features, and all the calibrations. The IMU state include the IMU orientation, IMU position, IMU velocity, and all the biases. For features, it includes all the points and all the planes. For caliber, it includes all the camera states, LiDAR, and wheel calibration. We want to point out that for the calibration, it includes both the spatial calibration and also the time of flight. How to handle asynchronous sensor measurements? And our solution is linear interpolation. For example, for pose at T0 and T1, the camera measurement happens at TS. In order to relate the camera measurements to the state of T0 and T1, we will first approximate the trajectory between T0 and T1 with the linear model, which assumes the omega and V is constant. Then we find the corresponding IMU poses at TS. In this way, we can find the interpolated rotation and position. We can see that to find the omega and V is the key for the linear pose interpolation. How to find them? The conventional way is to use the bonding poses. We can use the bonding orientation, compute omega, the bonding position, compute the V. Another way is, since we are using IMU, we can get omega and V from the IMU estimates. With the linear interpolation, we can add asynchronous sensor measurements to a graph. For IMU, we can build the pre-integration cost based on ACI square. For camera, we can build the image projection cost based on OpenVINS. For LiDAR, we can build the point-to-plane cost from Lake Fusion 2.0. For wheel, we can build the 2D odometry integration cost from Vivo. With all these costs, we can optimize the graph to get the best estimate of the calibration. In order to verify our system, we first design a simulation. We simulate one IMU, 3 camera, 1 LiDAR, and 1 wheel encoder in a structured environment. We both simulate 3D motion and 2D planar motions. All spatial, temporal, and intrinsic parameters are involved in the calibration. We want to point out that for all the sensors, they are designed with different frequencies and different time offset. We can see that under 3D motion, all the calibration, the camera calibration, LiDAR calibration, and wheel encoder calibration can converge nicely. However, in 2D planar motion, the calibration might fail. For example, the IMU cam translation. Sometimes the uncertainty and estimate errors is not improved at all. Similar case will happen for IMU LiDAR calibration and IMU wheel calibration. We further evaluate our system with real-world experiments on JECO. The JECO is equipped with multiple sensors like 1 LiDAR, 1 IMU, 1 wheel encoder, and 3 cameras. We first perform IMU with 3 cameras for calibration. All spatial temporal can converge. And we convey our results with calibrate. And the calibrate results is very similar to our results. We perform IMU camera LiDAR calibration. So IMU LiDAR calibration converges. And our results is similar to the results we get from MST call. We finally perform IMU cam wheel calibration. However, the IMU wheel calibration converts quite slow. So this is something we need to improve in the near future. Based on iCalib, we also realize multi-visual-inertial calibration, which can handle multi-asynchronous IMUs. And all IMU spatial temporal and intrinsic parameters are calibrated. We also study the degenerate motions for multi-IMU calibration. We perform 2 experiments, one based on microstring IMU, the other based on real sense with a low-end IMU. We can easily see that the microstring IMU has a much better accuracy than the real sense IMU. In summary, we designed iCalib, a multi-sensor calibration framework which can handle multiple IMUs, multiple gyros, multiple cameras, LiDAR, and wheel with both spatial temporal calibrations. We also studied degenerate motions for multi-sensor calibration. Both simulation and real world are used to evaluate our system. In the future, we will investigate camera calibration under constrained motions and improve the wheel encoder calibration. Thanks.